Hi guys, welcome back to Data Every Day. Today we're looking at a data set of Apple Store ranks from 2019, which is it's really an app store. The bunch of different apps with a bunch of different features, and we're going to be trying to predict the feed of a category. Of an app, which will be either free or paid, or grossing. But I think we're going to limit it to just free or paid. And we're going to using Logistic Regression to make our predictions. So let's load in NumPy and Pandas for dealing with the data, and then for pre-processing we're going to use the standard scalar and train test split function from sklearn. Then we'll import Logistic Regression, and we're going to be using this Logistic Regression CV classifier, which has some pretty cool features. So I'm going to load all this in and load in the data using pandas.readcsv, and we'll get the CSV file over here, ranks.csv. I'm going to copy the file path, paste it in, and take a look. And before we go any further, let's just get some information on the dataset. We can see we have no non-nulls. Looks like, no nulls. Looks like we don't have to worry about missing values. However, I see we have at least some because these negative ones are actually missing. Additionally, we have some columns that will not be of use to us. The app ID, the name, and the publisher we will not be using today. So let's start cleaning. Alright, first let's remove these unneeded columns. So unneeded columns equals app ID, name, publisher. Right, I don't need the ID because it's not giving me any information. The name and the publisher, technically I could extract some useful features out of it, but I'm not going to do that for the purposes of today's video. So data.drop unneeded columns from axis 1, and that's the new data. And then I also want to just replace these negative ones. So data.replace -1 numpy.nan. Now we're going to replace them with actual null values so that we can then check out how many null values we have in the dataset by doing data.isNA, which will just check if each value is NA, and you can see we have some null values here. If we sum across the rows, we'll get the number of each null value, null values in each column. And you see we have 800 null values in change and 8,200 in subchange. So let's go ahead and fill those in. For column in change and subchange, data subcolumn equals data subcolumn dot fill NA. So that's going to fill the missing values with a given value, and the value we'll give it is just going to be the mean of the column. So we're filling all the missing values with the mean of the other values in the column. Alright, let's print out the total number of missing values once we're done. So this time I'm going to sum over the rows, but then I'm going to sum over the columns as well this way so that we can get the total number. And we have no more remaining missing values. So now let's do some feature engineering. Take a look at data now. It's a little cleaner. You can see we have this date column that I'd like to get into individual features. We could construct a year, month, and day columns out of it. So data sub date currently looks like this. If we apply a lambda function to it, that takes in some x, which will be a single one of these strings, and it's going to return x from 0 to 4. This should just be the year, right? Since we don't have to worry about missing values, I'm going to just do the type conversion here, I'm going to make it an integer of the first 4 characters. And those are just the years. So what I'll do is I'll save that in a new column called year. Similarly, I'll do the same thing for month and for day. Now month is going to be not from 0 to 4, but from 5 to 7. That'll just target these two right here. And day is going to be the last 2 characters, so -2 to the end. Then data.drop date axis 1. We don't need the original date column anymore. And then before I move on, I actually noticed that this category column, even though it's a numerical value, if we look over here, you can see there's only 4 values it can take. So this is going to be best. Let's take a look at the unique values in it. Data subcategory.unique, and you can see there's only a couple values in here. So we're going to one-hot encode that column. One-hot encode just means we'll get the, for example, if we get the dummies using pandas.getDummies of the column, you can see it takes each one of these unique values and gives it its own column, and then each example it gets a 1 in whichever value it originally took, and 0s in all the others. So this is 24 new columns that we're going to add to our dataset. So what we can do is call this category dummies, and then we can say data equals pandas.concat, which will concatenate 2 data frames along a given axis. We're going to concatenate the original data frame and these new category dummies side by side, so axis 1. Also, I can also include a prefix here. Let's use cat as a prefix. What this will look like is it'll put cat at the beginning of the column, so we know that it's a category column. So I'll make that category dummies, and then I'll concatenate the original data like this and add these columns at the end. And then when we're done with that, we can drop the original category column. This is not useful to us anymore. Alright, let's take a look. And I believe we are fully done with our features. We just have to deal with these labels now. Encoding labels. Alright, why don't I add a little note? In fact, let's only worry about examples that are either free or paid. So I want to, this grossing value, I'm not going to worry about the grossing because I want to make this a simple binary classification task. And additionally, if we go into the feed column and get the value counts, which will get the number of times each unique value is found, you'll see that if we just cut out grossing, we'll have roughly a 50-50 split between free and paid, which is really nice for a classification. So let's query the dataset. We can query if grossing equals, if feed equals grossing. And this will be all the rows in which feed equals grossing. Now we can get the indices of this by index, and this will just be a list of the indices. So let's call it grossing indices. And then we can say data equals data.drop grossing indices. And this time axis is 0. Now whenever we drop rows, after we're done, we want to reset the index so that we get a proper index on the side here. And if we specify drop equals true, it won't use the old index as a new column. Alright, so We'll drop it, and then let's take a look at the value counts of the new one. Except I'm going to divide the value counts by the length of the column. And what that'll do is divide each one of these by the total number of examples, and we'll end up with a class distribution. So why don't I print that? Class distribution. Okay. So you can see it's roughly 50-50, 53-47 looks like. But now let's actually map it. So I'm going to create a mapping. That's going to map free to 0 and paid to 1. And so our new column is going to have zeros and ones, and we can do this very easily by data subfeed equals data subfeed dot replace label mapping. So you can actually pass a dictionary into the replace function that will apply the mapping to each element. Alright, and you can see our data is in fully numerical form now. All that's left to do is split and scale the data. So Y is going to be just the feed column, because that's what we're trying to predict. So we'll make a deep copy of it. And then X is going to be everything except the feed column. And we'll make a copy of that as well. Then we're going to create a new scalar object, which will be a standard scalar from sklearn. That will give each column mean 0 and unit variance. So X equals scalar.fit transform X. Now if we look at X as a data frame, because fit transform returns a NumPy array. You can see we lost the column names, but each column now has values between, most of the values lie between -1 and 1. Alright. And now we'll split into train and test sets. So this is using the train test split function. So split x and y into x train, x test, y train, y test. And let's use a train size of 100. No, 0.7. And include a random state so that we can reproduce the results. Okay, now we're ready to train. So I'm going to start with a logistic regression classifier. And we're going to fit it on the train set. And just going to do this very simply. When we're done, we're going to print out the accuracy, and I'll format the string here. To give us, here why don't I do this, base acc equals model.score on the test set. So it's going to evaluate it, get the accuracy on the test set. And we're going to plug in base acc into here. And this should be base model. Alright, and we got an accuracy of 97.6%. That's pretty good, especially for the base model, because now we're going to do a CV model. This is the Logistic Regression CV classifier. And what this will do is actually, it will use k-fold cross-validation. In this case, actually stratified k-fold cross-validation by default, which will just retain the class distribution of each fold. And it will actually perform a hyperparameter search for the inverse regularization strength, which is very useful. And it will find the best hyperparameter to use, and hopefully we'll get a better accuracy from that. So CV model.fit xtrain ytrain, and then CV acc equals CV model.score on the test set. Alright, and then we'll just plug this in again, except we'll do it on CVAC. And this one will take a little longer because it's going to be applying the k-fold cross-validation. But it shouldn't be too long. And you can see we have now an accuracy of 99.96%. And that's insane. That's really good. Yeah, so you can see that the cross-validation combined with the hyperparameter search really improves the results. So that will sum up today's video. Thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.